Start. So hi everyone. So I'm going to be talking a little bit about some work on probabilistic databases and approximations, and it's joint work together with Antoine and Kuldeep, who are both here today, so you can also ask them if you're interested in this. So when I first proposed this talk about intentional query evaluation, and I thought I would be the only one talking about intentional query evaluation at the workshop. It turns out yesterday, I saw over the weekend that Dan and Mikkel also had talks on this topic. And so this is actually quite closely related to what I'm going to be talking about today. The difference is that, very roughly, is that I'm going to be talking about compiling to less tractable circuits. So instead of compiling things like OBDDs or DDNNFs, I'm going to be talking about compiling to something called non-deterministic OBDDs and structured DNF circuits. And these are circuits that admit proximate counting rather than exact counting. And I'm going to be measuring everything in terms of combined complexity rather than data complexity, like was talked about yesterday. Okay. Also very relevant is Marcelo's talk tomorrow. So all of the approximation results that I'll be talking about here are actually using this FP-RAS for counting strings accepted by an automaton. And so, I mean, he'll give you the details of this tomorrow. Okay, so I'm going to start by just going over some background and reminding you about this probabilistic databases problem, talk a little bit about the complexity. Then I'm going to focus on the results. So I'm going to first look at developing approximation schemes when we don't restrict the database instance in any way. And then in the case where we restrict the instance, and then I'll be briefly talking about some lower bounds and inapproximability results, and then I'll conclude. So this is a standard relational model. I think everyone's seen this before. We're going to be looking at what are called Boolean conjunctive queries. So you can ask a question like, is there some x and y that satisfies both of these atoms? These are called Boolean conjunctive queries. If you know first-order logic, these are just existentially quantified positive conjunctive sentences. And that's what we're going to be focusing on here. I want to emphasize these are Boolean queries. So we're really interested in yes or no answers. We're not leaving any variables free here. So everything is Boolean. Okay. So that's a standard relational model. We can ask Boolean conjunctive queries on a database. But about maybe 20 years ago, Dalby and Succio noticed that this is sort of maybe a little bit under-equipped to deal with uncertainty. If you imagine the processes that populate these databases are often populated in a automated fashion, and they can be noisy. So you need some model that can deal with these probabilities. Okay. So the solution is very simple. You add probability labels to each of your tuples in your database. And the semantics are going to be as follows. You're sort of going to flip a coin with the given probability for every row. And with that probability, if it comes up tails, you're going to delete it. And if it comes up heads, you're going to keep it in your database. And you're interested now in asking the question of what is the probability that my original query, which is Boolean, is going to evaluate to true on this database that you sample. Okay. So you're basically just deleting rows from your original instance, and you're interested in knowing the final probability. So just to make this clear with an example, suppose, for example, we were to delete the second row here and the second row in here. That happens with these probabilities. Everything is independent, so we can multiply all these probabilities together to compute the probability of this subinstance. And it turns out this particular subinstance still satisfies the query that we had a couple slides ago. So we can just sum all of these up. Okay. So the problem of interest here that we're looking at is the probabilistic query evaluation problem. You're given a Boolean query and one of these tuple-independent probabilistic databases, and you're interested in finding out the query probability. So it's the sum of all probabilities of all the subinstances that satisfy your query. Okay. For the purpose of this talk, I'm going to be focusing on a special case of this, although everything extends to the weighted case, which is the uniform reliability problem. So that's where you give each tuple or each factor in your database a probability of a half. And if you think about it, then really what you're doing, it's the same thing as counting the number of subinstances that satisfy your query up to some constant factor. So what's known about this problem? So I think this was talked about a little bit about yesterday, but I'll just review. This is Sharpe hard in data complexity for most conjunctive queries. So that means when I fix a query and I look at my database as input, depending on the query I fix, this may be Sharpe hard or maybe polynomial time. For most queries, this is sharp p hard. And so the simplest example of such a query is if you take this RST query, then you can reduce from this plausibly partitioned 2DNF counting problem and show that this is sharp p hard. It turns out for a whole bunch of queries called the unsafe queries, you can always find such a reduction. And then for some queries, the so-called safe queries, you have polynomial time data complexity. Okay. So there's a polynomial time sharp p hard dichotomy result proved. And then with a little bit more work, you can extend this to UCQs. And that was done. Okay. What's interesting here is that the combined complexity of this is mostly still open, with I think the exception of one paper that looks at a special case of probabilistic graphs, which I'll talk about a bit later. But the combined complexity is really, it cannot be easier than data complexity, right? I mean, if your input query class has an unsafe query, then the combined complexity is going to be sharp. So already for data complexity, this is a very challenging problem, and in combined complexity, it's basically even harder. Okay. And then you have, as well as this, you have these results on intentional query evaluation. So most of these safe UCQs have a tractable representation of their provenance that's computable in polynomial time in the database size. Okay. So this is what Dan and Mikkel both talked about yesterday. Of course, there's this still open problem of whether all of these UCQs that are safe have such a tractable representation. But for most of them, we can get some tractable representation. So basically, for example, if you look at this example here, you have here a very simple query in this database. So we can compile this to an ordered binary decision diagram. And you can sort of imagine this as saying, well, okay, if I want my query to be true on any subinstance, well, I either need to have the tuples 1, 2, and 2, 3, or I need to have the tuples 2, 4, and 4, 4, and then I don't care about the other tuples. So that's effectively what this binary decision diagram is encoding. And so if you do your model counting process on this binary decision diagram, which can be done in polynomial time, then you get your uniform reliability. And if you do weighted model counting, you can do the probabilistic query evaluation. Okay, so that's sort of the state of the art, I guess, in terms of exact. But then there's sort of a natural question is like, now we're in deterministic query evaluation, we're computing yes or no. Now in probabilistic databases, we're computing a number. So it's a natural question to ask, can we approximate this number? So can we approximate the probability of a query? Okay. And the other thing is that, as I mentioned, most of these results are written in terms of data complexity. So it'd be nice if we could sort of find places where there's also not such an exponential dependence on the query. Okay. So the question is, can we get a larger class of tractable queries with polynomial dependence on both the query and the database size by allowing for randomized approximations? So to formalize this a little bit is what query classes Q and instant classes D can we get an algorithm such that for any epsilon and delta you give me and any queries and databases from these classes, I can compute the probability of this query on this database within a 1 plus minus epsilon error factor with 1 minus delta probability, and a runtime that's polynomial that's both in the query and the database. Okay. And I'm going to call an algorithm that satisfies these conditions a combined FP-RAS. Okay, so combined because it's both polynomial dependence in Q and in D. Okay, and the interesting thing here is that we're going to be, to find these combined FP-RASes, I'm going to be taking a fully intentional approach. So I'm going to be compiling these queries and instances together to circuits that are of combined polynomial size. And I'm going to be focusing as my target circuits that are known to admit an FP-RAS by the recent result of Marcelo that he's going to be talking about tomorrow. Okay, so currently these circuit classes are non-deterministic OBDDs, which I'll talk about in a minute, and structured D and F circuits. Okay, but before we go there, I just want to motivate a little bit better, like why we're looking at both query and instance size. So one question you could ask is, maybe I don't care so much about the dependence on the query, and I'm happy just with the polynomial dependence on the database alone. So if you do that and you relax this runtime restriction to only have a polynomial dependence on the database, it turns out you can actually get an FP-RAS for all UCQs and any instance by computing the provenance of the query in DNF. Okay, and DNF is known to admit an FP-RAS by a very old result. But the problem with this is that the size of this DNF has a exponential dependency that looks like this. So basically, you've got the query in the exponent here, and your database is usually in practice quite large. So if you had, for example, a database with a few hundred tuples and only 5-atom query, you're going to end up with a DNF of over 1 trillion clauses, and so this is really infeasible to materialize. So even if you have a great DNF counter, you're not even going to be able to write out the DNF. So that's why we're really looking for a dependence that's polynomial on both the query and the database. Okay, so a couple observations. First, very obvious observation, I guess, is that if your query class, your database class, emits tractable exact probabilistic query evaluation, then of course you have a combined FP-RAS. The other one that's maybe slightly less obvious, but still worth mentioning here, is that if your query and database class admits a combined FP-RAS in the sense that we talked about it a moment ago, then they cannot have NP-hard combined complexity for deterministic query evaluation. So why is that? Okay, suppose what you can do is you can say, let's say Q and D have NP-hard combined complexity. Okay, then we could run our combined FP-RAS on tuple-independent database where all the probabilities are 1. Then you sort of are saying, well, MP is in BPP, and so RP equals MP. Okay, so basically, you're just reducing this probabilistic database problem. I mean, you can sort of see it as the deterministic query evaluation problem. You can see it as a special case of the probabilistic query evaluation problem in some sense. Okay. So the first setting I want to talk about is where I make no assumptions on the database instance. Okay. And then the result we can get is as follows. So any query you give me, which is self-join free and has bounded hypertree width, I can get a combined FP-RAS for this. Okay. And the reason for this is, well, we need the bounded hypertree width because this is a sufficient condition to guarantee a deterministic query evaluation. Okay. And so really the only extra restriction I have here is the self-join freeness. Okay. So I'll sort of sketch how you get this result. And the idea is that, like I said, we're going to be taking an intentional approach. So we're going to be constructing a non-deterministic OBDD that represents the provenance of the query. Okay, so we're really going to be harnessing the power of the ability to add disjunctions to my OBDDs. Okay. And so what is a non-deterministic OBDD? Well, it's just an OBDD, but I can put in OR nodes. Okay, and the OR nodes basically just mean what you think they mean. It means that I can basically make a non-deterministic choice of whether I go to the left or to the right. Okay. How does the construction work? So if you take a look here at my query, because this is self-join free, I can sort of split it into 3 layers, one for each atom. And I'm first going to look at the first atom, okay? And essentially, I'm going to look at the possible matches of this query, and I can sort of say, okay, well, for this query to evaluate to true, either I can go 1, 2, 2, 3, 3, 3, something like that, or I could go 2, 2, 2, 3, 3, 3, and so on. But effectively, the only things that are going to lead me to a positive answer to this query are going to be either by taking the first row or the third row. Okay, so I can make this non-deterministic choice of where I go here. Okay, so I can go either I have R12 or I have R22. Okay. Now, every single possible answer to this query, if you take a look at this instance, also has to pass through 2, 3 here. So we have the 1 nodes going through here through 2, 3, and then so on. And then again, we can use disjunction here. Once I get to 2, 3, I can make a non-deterministic choice of whether I'm going to have 3, 3 or 3, 4 as my witnessing tuple. Okay. So we're just basically using disjunction in the NOBDD, and it turns out we can then now get something that's a polynomial size both in the query and the database. Okay. Now, by the fact that non-deterministic OBDDs, you can approximate the number of models, you now have your FP-RAS for probabilistic query evaluation. So the second case that I'm going to look at here is ask, okay, now that works for any database instance you give me. Now what if I want to put some restrictions on the database instance class? Then can I maybe get a more expressive class of queries that don't have the self-join free restriction? Okay. So I'm going to be looking at a special case of probabilistic database, and that's probabilistic graphs. Okay. So that's where I'm going to restrict my query and my instance to a binary signature. Okay. So now I've instead of using Q for query, I'm going to say G, and instance, I'm going to, instead of saying D, I'm going to say H. And you can sort of look at these as graphs, and H is going to be annotated with probability values on all of the edges. Okay. And I'm going to compute the probability, essentially, that a subgraph of H emits a homomorphism from G. And if you think about what this is asking, it's the same thing as evaluating a query on a database over a binary signature. Okay. And you can distinguish in this case between two settings. So you can have the labeled setting, which is really where we are in probabilistic databases, where I place no restrictions on the number of relations I have in my signature. But you can also look, because this is graphs, it's sort of interesting also to look at the unlabeled setting. So in this setting, I have a fixed signature, and I have only one relation appearing in it. And I'm going to look at quite a large variety of different graph classes here. Okay, so I'm going to look at these classes here. So I'll briefly sketch out what these classes are. So the first classes are what are called one-way path classes. Okay, so these are just path queries with all the edges going in one direction. We also have two-way path queries with sort of the same thing, but we now allow edges to go in a different direction. We also look at downwards tree queries. So these are basically a directed tree where all of my edges are pointing away from the root of the tree. Polytrees, which are the same thing as this, except here I don't place any restriction on which way the edges point. So I could have some of the edges pointing towards the root and some away from the root. Directed acyclic graphs, so that's what you think it is. And then connected directed graphs, so just arbitrary directed graphs, basically. Okay. And depending on the restrictions I place on my query graph and my instance graph, I can get a whole bunch of different approximability and inapproximability results. Okay. So again, this is all in combined complexity. I've split it up here into two tables. One is the labeled case. So this is the standard probabilistic database setting where I place no restrictions on the number of relations I use. And one is the unlabeled setting where I have only one relation. And in this table, I've sort of got three colors here. I don't know how well the gray shows up here. But effectively, what this means is that if I, for example, have a query here, a one-way path query on a one-way path instance, if this is white here, then that means that this is in polynomial time in combined complexity. So these results actually are already known. But what's new here is that we now also have approximability results. So the light gray here means that, for example, if I have a one-way path query and a polytree or a DAG instance, then although this is Sharpie hard, there is now an FP-RAS for this, okay? And I'll show how we get this FP-RAS in a minute. For the ones that are in black here, these are ones that are Sharpie hard, but we also know, we can provably show that there's no FP-RAS for these settings, subject to standard complexity theoretic assumptions, okay? And again, it's the same thing for the unlabeled case, although you have a little bit more that's tractable in the unlabeled case because you have this restriction that you only have one relation. So I'm just going to sort of highlight one particular FP-RAS result because it turns out that it's really effectively the only FP-RAS result we have here. This is essentially looking at one-way path queries on labeled directed acyclic graphs. And so the result here says that any one-way path query on any labeled directed acyclic graph, I can get a combined FP-RAS for this problem. And it's the same idea as what we had a few slides ago. We're going to be constructing a non-deterministic OBDD that represents the provenance. And then we'll appeal to this sharp NFA result that I mentioned earlier. And the ordering that we're going to get in this NOBDD is going to be given by a topological ordering of the edges of the DAG. And you'll see how this comes in just a second. So here's, for an example, here's a query. I have a query of length 3. You'll notice this is not self-joint free anymore. So now I allow, for example, R appearing twice here. And I've written this just in the graph notation here. So this is the exact same thing as saying RXY, RYZ, SZW, for example. And then now I've also written my instance in this sort of graph notation just to make it a little bit easier to read. And the idea what we're going to do is we're going to basically take the disjunction of the non-deterministic OBDD corresponding to all the possible starting points of a match of the query. So for example, I could have a path of length 3 that starts at 1 here, that goes, for example, R, R, and then S. Or I could, for example, go R, R, and S. Or I could start at 4 here and then go R, R, S. I could start at 4 here and go R, R, S. So I'm going to consider all the possible starting points. I'm going to take their disjunction, and for each possible starting point, I'm going to build an NOBDD. So let's just see the example for one possible starting point, which is at point 1. So if you think about it here, it's really just the same idea. I mean, we know here we're forced to take R12 to start, and then we have a choice, right? So we can either go towards 5 or we can go towards 3. So we have this disjunction here, okay? And then once I, for example, pick to take this route in this split here, then I'm sort of forced to go to 5, 6. So that's what you see here, for example, R12, 2, 5, and then 5, 6, and then I've got a match. So we're really taking advantage of the determinism of the non-determinism here and the ability to add disjunction to deal with these cases in the directed acyclic graph instance where I have an out degree of more than 1. Okay. So that's the case for the path starting at node 1. Really, the only other possible place I can start in this graph just to get a match would be node 4. And it's really exactly the same thing, except here we're replacing this first edge with 4, 2 instead of 1, 2. And then everything else in the NOBDD remains the same. Okay, and then the nice thing about this is that from this, we can also get an extra result from this. So you can also get a result on a problem from operations research called two-terminal network reliability, or ST reliability. So this is a problem where you're given a directed graph with independent edge probability labels. And you basically want to compute the probability that if you randomly sample a subgraph according to this distribution, that you can get a path between the two terminals you specified, okay? And the cool thing is that using the construction that I just showed, or something very similar, is that you get an FPRAS for this ST reliability problem on DAGs. And this is a problem that was open for some time. And and independently, I think Wei Ming, who's here, also found an FPRAS for this problem very recently. And so the idea is that here we're going to take a disjunction over all of the connecting paths of different lengths. So in this case, you can see, for example, if I specify 1 and 6 as my two terminal nodes, any possible path from 1 to 6 is going to have length 3. So I can only just focus on the case where I have a path of length 3. And we can construct an NOBDD using the same idea. And we're sort of basically enforcing that I start at 1 and I end at 6. And again, we're just using this disjunction idea whenever I need to make this non-deterministic choice of where I go. Okay, and then I also want to talk a little bit about lower bounds, so inapproximability results as well. So one natural question that you could have when you see this is that, could it be the case that everything that's tractable in a combined complexity for deterministic query evaluation also admits a combined FPRAS for probabilistic query evaluation? Okay. So for example, bounded hypertree width, we know that's a sufficient condition to guarantee tractable exact query or deterministic query evaluation. Could it be the case that everything with bounded hypertree width, I can also get a combined FPRAS for probabilistic query evaluation, the probabilistic query evaluation problem? The answer, in fact, is no. And in fact, already in a very restricted case, we can show the following. We can show that, again, subject to some complexity theoretic assumptions, even on a fixed signature with only a single binary relation, so like an unlabeled graph, for example, there is no FPRAS to approximate the probability of a tree width 1 conjunctive query on a tree width 1 instance. Okay. So it turns out that basically like getting these combined FPRASs is in fact quite difficult. And if you're interested in how this is proved, very roughly the sketch for this is you reduce from monotone 2CNF of bounded degree and to this probabilistic query evaluation. Another question is about the circuit sizes. Okay, so I mean, we're constructing these circuits and to get all of these results. So, I mean, although it's possible that I mean, we know there's no FPRAS existing, but could it be that there are still small circuits, right? It just might take exponential time to compute these circuits or these NOBDDs. So could it be the case that you have these compact representations of provenance always existing, despite sometimes being hard to compute? And the answer again here is no. So it turns out that you can show that that there's an infinite family of path queries and an infinite family of instances, such that any DNNF circuit capturing the provenance of these queries on these databases must have exponential size. And in particular, this already holds for DNNF circuits. So this also implies exponential lower bounds for more tractable forms, so things like DDNNFs, structured DNNFs, and so on. And also, this is sort of interesting because these are path queries, right? So we know that path queries are linear time combined complexity to evaluate exactly, but to get even just a mildly tractable representation of their provenance, we need something that's exponentially sized. So again, very roughly, if you're interested in the details of how this is proved, you can find families of monotone 2CNFs that have bounded variable occurrence, but their smallest DNNF is exponentially sized. And then by using the reduction in our previous result, you just look at the query instance families you get, and that gives you these families. Okay, so I think I'm just about out of time, so I'll just wrap up. There's lots of interesting directions here that I see for future work. So the most obvious one is generalizing these results. So a lot of these results that I showed were for probabilistic graphs. So it'd be interesting to generalize this to like higher arity instances. And the main positive result we had on these graphs were on DAGs. So there is notions of like, for example, bounded DAG width. I don't know if it generalizes to that or not. Maybe someone who knows more about that can tell me. And also obviously to more expressive queries. So everything we looked at were just conjunctive queries. You can also ask about things like negation, recursion, and so on. Another natural question is, so we compile to NOBDDs, which are really just a special case of structured DNNF. And it's also natural to ask what other formalisms admit tractable approximate counting, okay? So for example, could we get a result for unstructured DNNF circuits? So maybe Marcelo will have some ideas on that when he talks tomorrow. And if so, what are the implications for probabilistic query evaluation? So can we find queries that have small unstructured DNNF circuits, even though they might have large structured DNNF circuits? Also because, I know a lot of people at the workshop are from an AI background. I think this result is quite interesting because it gives us a very easy and lazy way to get an FP-RAS without having to get our hands dirty. And so could you apply this FP-RAS here to other problems in AI? So for example, in graphical models, or for model counting on general circuits, getting parameterized counting results. There's been a little bit of work on that on a parameter called CV width, which gives you a parameter on CNFs to compile to structured DNNF. And then the last thing is making all of this practical. So now these are some interesting applications of this non-deterministic OBDD result. So I think these results sort of motivate the development of like a practical approximate counter for structured DNNF circuits. So I think with that, I'm just about out of time, so I'll conclude. Thanks.
Do we have questions? Yeah, so suppose you do have free variables. So have you thought about the problem of sampling from the space of outputs? It's also related to Marcelo's talk a couple of weeks ago about the sampling from deterministic queries.
I guess the short answer is no. I haven't thought about that. So I guess here we're really assuming everything is a Boolean query, because that's usually in probabilistic database. These are sort of the semantics that people look at. Maybe there's been work that generalizes this to allow for free variables, or maybe there's a natural generalization. But off the top of my head, I don't know.
Okay.
Yeah, so one an orthogonal type of open problems is to characterize the data complexity for approximation. but for universally quantified queries
Yes.
that are found in knowledge representations like Markov logic networks. Does your work give us any insight into that problem, which, as far as I know, is completely open?
Yes, I've thought about this problem as well. As far as I know, it's open. I don't see directly how to apply this to I mean, effectively, I guess it would be like applying this to queries with negation is what the equivalent thing would be, I guess, in disjunction.
Right. If you put the negation at the very top.
Negation.
Yeah.
Yeah. It's an interesting question. We didn't look at it yet, but that's sort of the logical next step. So I think, looking at negation, and then you would, it's an interesting question, but we haven't thought about it yet.
Other questions? So I actually have a question. Like, are these FP-RAS actually tractable from a practical point of view? Like, can you actually?
I think currently my understanding is no, but I know I've talked to at least 3 or 4 people here who are all independently saying they're working on this. So
Right.
I'm pretty confident that hopefully in a couple of years we'll have something that.
Okay, great. It's recorded, right? Right. Do we have more questions?
Push, but it's already pushed. This may be a weird questions or not. So I'm working on Bayesian network, not on probabilistic databases. So the corresponding questions, when instead of the data being a database, being Bayesian network, did you think about the class of questions, answering queries, the tractability of those Boolean queries over a Bayesian network?
I have not thought about that, but when I wrote the slide here, I did think about this question because effectively, I guess the main message here is that you now have a very easy way to reduce to this problem, to this, by building a circuit, you now can do approximation. And so this is one application of that. But for example, you could ask the same question, is there some parameter, maybe something less restrictive than tree width, for example, because tree width gives you exact tractability in Bayesian networks. There's some less restrictive parameter for Bayesian networks such that you can compile to a circuit, for example, like one of these circuits, and then use the FP-RAS there. So that's sort of what I was thinking along the lines here.
Actually, you can use hypertree for Bayesian network because this is conjunctive queries with weight. So this is the same problem.
I'm not sure because tree width, yes, hypertree width, I'm not sure. For probabilistic queries, yeah, okay. Just a comment. So there is work about answering constraint-based network, constraint questions, which is Boolean questions on Bayesian network without, translating to circuits. You can also do it that way, but you are right that the tractability is based on the tree width.
Yeah.
Other questions? No? Okay, so let's thank the speaker again. We take